Welcome back. And in this last section, we're going to be looking at the application of redox potentials to storage cells. So that's batteries, basically. We're going to look at the lead accumulator battery. We're also going to look at hydrogen fuel cells and alcohol fuel cells. So you're going to need your notes, and we're on page 17, where we're going to be looking at storage cells. So a storage cell is one of the electrochemical cells that we've been looking at, but it's based on a reversible chemical change. In other words, it can be recharged, plugging it into an external electricity supply. So examples of this would be the batteries that power your phone. So once the chemistry has run out, once we run out of chemicals in the phone, the battery needs recharging. To do that, to run the chemistry the wrong way round, we plug it into that external electricity supply to charge up your phone. So an example of this is given on page 17. So this system is set up, and because we're using the battery to power something, we call this discharge. So this is discharge. So this would be basically you using your mobile phone. So here I have this reaction going on at the negative electrode. So the lithium metal is becoming lithium ions. So this is your oxidation. This occurs at the anode. And in this case, the anode is the negative electrode. On the opposite side, we have our positive electrode. This is our reduction reaction. This is the gain of electrons. So this is reduction reaction. This is where the cathode. And this is my positive electrode. So given the reactions for discharge, we should be able to work out the reactions for charging. Remember, charging is basically the reverse of the discharging reactions. So here I've got lithium turning into lithium ions. So when I recharge my phone, those lithium ions are being turned back into lithium atoms, and they are gaining 2 electrons. So this reaction here is my reduction reaction. This time the reduction reaction again is happening at the cathode, but this time the cathode is the negative electrode. Notice reduction always occurs at the cathode regardless of the sign, but charging is very much like electrolysis. So electrolysis and charging, the same idea. You've got an external power source which is driving the reaction. And that's the process you've mostly done at GCSE, electrolysis. So in electrolysis, the cathode is the negative electrode because it attracts the cations, but that's just for charging. Remember, for discharging, the cathode is the positive electrode. Obviously, on the other side, we've basically got the same reaction as we had before, only we are reversing it. So I have my lithium oxide and my Mn2O3, and that is going to my 2MnO plus my 2 electrons plus my 2 Li positives. So that is my oxidation reaction. That will always occur at the anode, and in this case, my anode is my positive electrode. So these aren't actually lead acid accumulator batteries, but you'll see one of those in class. But they do explain the difference between a galvanic cell, which is when I'm doing discharging, and electrolytic cell when we're doing charging. So this is the one you're probably more familiar with from GCSE and also from physics, where you plug things into your external power source. But this is the one we're more interested in chemistry, because this is where we can release energy via the spontaneous or feasible redox reaction. And we can convert that redox reaction into electrical energy to run things like a car starter motor or a light or a phone or something else. once the chemistry has been depleted. In other words, once everything has gone from this side to this side, you need some way of recharging it. So this side then is when we recharge it. So this is what happens when you're using your mobile phone, and eventually those little lines go down and down and down, and you're told that you've run out of battery and you need to recharge it. This is what's happening when you're recharging your phone. You're plugging it into the external power source and you're driving the reaction in the non-spontaneous direction. So our overall cell reaction is here. Delta G is less than 0, it's a negative number, so this reaction is feasible. Notice it's the reverse of this reaction, where delta G is greater than 0, it's a non-spontaneous reaction. And that's why I have to use a powerful external source of energy, in other words the electricity supply, to drive it in the opposite direction. Now for the lead acid accumulator, we obviously have charging and discharging. When we're charging the phone or the lead acid accumulator, notice this is a lot like electrolysis. So the oxidation is occurring at the anode, and the anode is the positive electrode, and reduction is occurring at the cathode, and the cathode is the negative electrode. When we're discharging it, when we're actually using our battery to run in the spontaneous direction, then the anode, again, oxidation is still happening at the anode and reduction at the cathode, but notice now the anode is the negative electrode and the cathode is the positive electrode. So we're on page 19 of your notes and we're looking at hydrogen fuel cells. So there are two types of hydrogen fuel cells you need to know about. One is the alkali fuel cell and the other is the acidic fuel cell. The only difference between these two is the electrolyte. In the alkali fuel cell, the electrolyte is OH negative ions. In the acid fuel cell, they are hydrogen ions. And in this case, the electrolytes are going from the cathode to the anode. And in this case, the electrolyte are going from the anode to the cathode. But that's the only difference. The overall reaction for both of them is the same. It's hydrogen plus oxygen giving water and obviously releasing that energy which you can use to drive something like a car or other vehicles. These are mostly used in vehicles. Notice these are all discharging because you're discharging, you're using the reaction in the spontaneous direction. So my oxidation is occurring at the anode in my alkali fuel cell, and it's the OH negatives which are moving across to the anode. So I have my hydrogen and I have my OH negatives, and they are forming water, and because it's oxidation, you're losing the 2 electrons. And the other side, we've got the reduction reaction. This is my positive electrode, and here my oxygen and my water are being reduced to those OH negative ions and my 4 electrons. And in here, my electrolyte is obviously my OH negative because this is an alkali fuel cell. Now when I put these two half equations together, notice I've got to times this one by 2, so I get 2H2 plus 4OH negative plus O2 plus 2H2O goes to 4H2O and 4OH negatives. Should be very easy to see. You can cancel some things. So you can cancel the OH negatives because they're the electrolytes, they pass across. 2 of the waters get cancelled here, and we just get 2H2 plus O2 going to 2H2O. So overall we're combining hydrogen and oxygen to make water. So remember, in the acid fuel cell, the electrolyte is the acids. So again, we've got oxidation occurring at the anode. You've got your hydrogen turning into your hydrogen ions and releasing those electrons. Electrons passing around the external circuit to join with the oxygen. So I've got my oxygen, which is gaining as well those hydrogen ions and the electrons to become water. Again, if I combine these two half equations together, I simply get H2 plus half O2 going to H2O. In other words, it's exactly the same as this top reaction. So exactly the same reaction is going on, which is why you get the same overall reaction. The same overall reaction here, no matter whether you've got an alkali fuel cell or an acid fuel cell. So we don't just have to use hydrogen as a fuel, we could also use alcohol. So we can use methanol or ethanol in the place of hydrogen. But again, the same principle results. I'm basically taking my alcohol and I'm oxidizing it. So again, this is my negative terminal because again, we're doing discharging. So the oxidation occurs at the anode, which is the negative terminal. The positive terminal, the reduction reaction is going on, and this is happening at the cathode. Again, what I would need to do is combine these two half equations. So I have CH3OH plus 6H positives plus 1.5 O2 plus H2O goes to CO2 and 6H positives and 3H2O. And again, I can cancel the electrolytes, cancels, one of the waters cancels, and I get CH3OH plus 1.5 O2 going to CO2 and 2H2O. In other words, the full oxidation of methanol or the combustion of methanol. So all we're doing is we're burning methanol, but we're burning it under very controlled conditions where we've split the two half reactions up so we can use the electrons to drive a car or a battery. So again, we can do exactly the same reaction, but using ethanol in place of methanol. It will just balance slightly differently. But overall, you've got the same full oxidation of the alcohol to carbon dioxide, or you've basically just got the combustion of the alcohol to carbon dioxide and water. So there are advantages and disadvantages to using these fuel cells. One of the biggest advantages is their efficiency. They are much more efficient than petrol engines. So they can convert chemical energy into electrical energy in about a 70% efficiency, whereas petrol engines only have about a 40% efficiency. So a lot of the energy from the petrol engines is wasted as heat. We don't waste as much energy in our electrical fuel cells. They are expensive, usually because of the cost of the catalyst, although this is coming down and down, which is why we're seeing far more electric cars and why we're seeing far more cars based on fuel cells. There's less pollution, as the only product at point of use is water. It's not carbon neutral, please notice, because you still have to make the hydrogen, and that tends to be very inefficient and produces a lot amount of carbon dioxide. Hydrogen has a high energy density per gram, but a poor energy density per centimetre cubed. Storage and transportation of hydrogen are the biggest problems. A few years ago, hydrogen fuel cells were going to be the way forwards, and we were expecting cars to be driven using hydrogen fuel cells. That hasn't happened because of the problems of storage and transportation. What has happened is the fuel cells using batteries have become much more efficient. They've come down in price, and that is why we're not seeing as many hydrogen-driven vehicles, but we are seeing a lot more of the battery-driven. Another reason for why hydrogen fuel cells haven't taken off in the way that we thought they might have done a few years ago is the infrastructure. There are very few hydrogen refueling areas in the country, whereas you can, although it takes a long time, plug your electric car into your power supply from your home. It would take several hours or overnight to recharge it, but it is possible, whereas it's not possible to have a hydrogen fueling station at home.